So good day everyone. Welcome to this video lecture. So as an introduction, I'll show you this figure here, which shows the trend in increase in published research over the past 30 years. So clearly there's a boom in the number of studies or researches, and you can see there's an exponential increase to be specific. So basically a certain topic, if you search for a certain topic in databases such as PubMed, you will be overwhelmed with the amount of evidence that it returns in its search results. And really, it's a lot to go through, especially if you want to concentrate or focus on a particular aspect of the research on that topic that you're interested in. But because of the volume, this can be very time consuming. Now, if we're to put this in numbers, it'll be like this. So the information explosion basically involves having more than 100,000 published articles each year in more than 20,000 journals. Okay? Now, here's just to give you one example. So there are many published studies testing the same or similar hypothesis, yielding contradictory results. A couple of examples would be use of high-dose vitamin C during a cold and use of allopurinol during a gouty attack. So you search for those in databases such as PubMed, and you will be overwhelmed with the amount of information there is about this particular topic, or these particular topics for that matter. Now, to complicate things, a particular topic has a very complex body of literatures, which is kind of expected because as experts learn more about the disease process or a particular topic, of course, the relationships between variables, relationships between pieces of information become more intricate and more complicated. Hence, you have this. Okay. So basically, there has to be a way of reviewing all the data and results from research about a particular question in a standardized, systematic way. And because of this, enter systematic reviews and meta-analyses, which were developed sometime in the mid to late 1970s. So I'll talk more about that in a bit. Okay, so now the approach that I'll be taking in this video lecture will be basically the same as what I did with my video lecture on RCTs. So I already had prior videos that covered the basics of systematic reviews and meta-analyses. So in this video, I will basically be delivering information about systematic reviews and meta-analysis in such a way that it familiarizes you on how to perform them, just in case your group decides to perform a systematic review or meta-analysis as your research project as you go along in the medical research curriculum. Okay, right. So to begin with, systematic reviews and meta-analyses are often used interchangeably, but they are actually not the same. So I'll be defining them from this point on. So what are systematic reviews? So the definition kind of sounds a bit repetitive when because I used the word systematic twice, both in the term and in the definition. So a systematic review is basically a systematic search for all available studies. And when we say systematic, it means that we are making use of replicable search strategies. So we actually have keywords or search words or search keywords that we type in the database, and basically what it means is if you give these keywords in the same order or in the same format that you typed in the search engine, and you give it to somebody else, and then that other person uses those keyword or key search words in the same database, that other person should get the same amount and the same number of studies in his own search, the same as you did in your own independent search. So that's basically what it means. And once you've gathered all of those available studies, you summarize all of this empirical evidences to answer your particular research question. So you just don't gather all of the research papers just like that. So there has to be a certain eligibility criteria for including such papers, and that eligibility criteria should be based on your research question that you have structured using the PICO or PECO format. Okay, so you'll notice here that I actually put in brackets PECO with an asterisk because systematic reviews and meta-analyses were originally intended for combining different RCTs. Though over time, there are more contemporary forms of meta-analyses that now include non-experimental or observational studies that you pull together. Okay, right. So a systematic review is basically a bringing together of all the different studies that fit a pre-specified eligibility criteria that you have set, basing on your own research question. Okay. That's not just a hodgepodge thing that you do. So, if you plan on doing a systematic review, you have to critically appraise uh, the material or the contents in the papers that you gather together. So you have to critique the methodology, be objective about it, um, check for scientific soundness or applicability of the methodology to your research question, and you also have to see or look at these individual studies, whether the analysis was done appropriately, and so on and so forth. Okay, so you have to be comprehensive and critical and objective about the review of all the papers that you gather, right? So lastly, a systematic review can synthesize the results with or without a meta-analysis. Okay, and the synthesis of all the papers in your systematic review, in your final systematic review, is narrative in nature. Okay. Now, how about with meta-analyses? So basically, what are meta-analyses? To start off, the term meta-analysis was first coined in 1976 by a doctor researcher, Jean Glass, to refer to the statistical analysis of a large collection of analysis results from individual studies for the purpose of integrating the findings. Okay, and the suffix meta that is attached to the word analysis kind of gives it a meaning that translates into analysis of the different analyses that were done. Okay? Unlike systematic reviews, meta-analyses use math. They use statistical methods of combining, or the more proper term for that is pooling, the results of more than one study to find the average or common effect across studies, which is expressed mathematically. Okay, so you've encountered some of the, or you've already encountered treatment effect measures or measures of association in your previous videos. You have your risk ratio, odds ratio, prevalence ratio. So basically, what meta-analyses do is they combine the data mathematically from the different studies, and they come up with a pooled average or overall summary risk ratio or odds ratio or what have you. We'll go through that later. Okay, so we will touch on these statistical methods a bit, just enough that you understand what they're for. You don't have to really know about the intricate details on how to perform these statistical methods, since you already have software to do that for you. Okay. Now, just as with systematic reviews, there you have to set pre-specified eligibility criteria for the studies you want to combine in a meta-analysis. Okay. Make sure that you're combining apples and apples or oranges with oranges and not combining apples with oranges, so to say. Meaning you are actually combining homogeneous studies or studies that are actually testing the same hypothesis using this more or less the same methodologies. Okay, because if you inappropriately combine heterogeneous studies, in a manner of speaking, combining oranges and apples, then you may actually get unreliable results for your meta-analysis. Okay. Again, as with systematic reviews, you have to be critical in your appraisal of the studies that you collect. Okay, you have to be objective. You have to give a comprehensive review, right? And reflexively, meta-analyses can also be presented with or without a systematic review. So we've already defined systematic reviews previously in this lecture. Now, at this point, you should already be aware that research involves, to some extent, some basic statistics, which you use to do hypothesis testing. Okay, you want to see if there are statistically significant findings in your results or not through the use of or through performing statistical testing using basic statistical methods. Okay. Now, with meta-analyses, though, significance testing is not really well suited because, for one thing, meta-analyses or the pooled estimates that you will derive from meta-analyses uh, is highly dependent on the sample size. Okay, of course, the higher the sample size that you will gather, the better the precision and accuracy of the uh, pooled estimates, assuming you've uh, combined you assuming the studies that you've retrieved for your meta-analysis all satisfy the same eligibility criteria that you've set, and they're all homogeneous in a way and not heterogeneous. Okay, basically meta-analyses focus rather on the direction and magnitude of the effects across studies. So is the direction of the effect gearing more towards benefit from the intervention, or is there benefit more from the placebo instead? Okay, and you also want to see the magnitude. How big is the effect? Okay, and uh, whether or not there is a statistical difference between effect measures between the intervention and the placebo group. Because again, take note, meta-analyses were initially intended for combining different RCTs together. Okay, so the direction and magnitude of the treatment effects or effect measures are represented by the so-called effect size. Okay, we'll be going back to that term again later in this video lecture. We report effect size estimates in meta-analyses, and we very often include what we call confidence intervals. Okay, so I'll show you how confidence intervals are represented in the results in meta-analysis, and basically whether or not the confidence intervals cross the so-called null value, and where the direction of the overall effect is would be helpful for us in finding out if the pooled estimates of the studies actually show benefit from the treatment or benefit from the placebo or harm from the treatment or what have you. Okay, so we also have a pooled effect size involved in meta-analysis results as well. So we'll go back to those later in this talk. Now, when is performing systematic reviews and or meta-analysis indicated? So it becomes appropriate to perform SRMAs or systematic reviews and meta-analyses whenever there are multiple studies available or published which test the same or similar hypotheses, and their joint results do not clearly indicate the results of the test, meaning the results appear to be vague. They seem to say that, it's suggestive of benefit, but not really. It's suggestive of harm, but not really. It's not quite clear. Again, this is all sample size dependent. Okay, so that can be one indication wherein you perform a systematic review and meta-analysis to critically appraise all these RCTs that were done to address the same hypothesis. And then by pooling the estimates together, we can see now with more precision where the direction and magnitude of effect is. Is it towards benefit afforded by the treatment, or is it towards harm? Okay. We also do SRMAs when there are numerous studies or numerous similar studies that have contradictory results. So there will be some studies or some RCTs testing the same thing, showing beneficial results. There will be some showing not so beneficial results. So in order to resolve this contradiction, let's combine them in a meta-analysis and see once and for all what the pooled effect is. Okay, of course, you have to keep in mind the eligibility criteria of combining the papers that you select. Okay, and also you perform this, and this is more for systematic reviews. You perform this when you want to summarize or review complex bodies of literature. So you want to summarize everything, or in an article, or in a systematic review article. Okay. Okay. Now, when is it not appropriate to perform systematic reviews and meta-analyses? So it's not appropriate to perform them if a collection of studies that are included uh, are not suitable to be combined in the first place. That's what I've been alluding to as combining apples and oranges, meaning the different studies that you collected or retrieved and combined are actually quite heterogeneous in one way or another, maybe in terms of their methodologies, maybe in terms of their comparators. So basically, when does this happen? So this happens when the studies or the outcomes that are being measured in the studies are too clinically diverse to combine. Okay, so you have to take note of that. That is why you have to read and critically appraise every single study that you retrieve, that you wish to combine or include in your meta-analysis. Of course, basing on your research research question. Okay, so it would be another instance. So this also becomes a case when studies have different comparators and you combine them. So that perhaps may not be an appropriate thing to do. Okay. This also happens when you combine studies that have different study designs. So basically, you do not pull together RCTs and cohort observational studies in one meta-analysis. So at least in my book, that is inappropriate. Better yet, just pull together RCTs alone, just pull to and do a different analysis, pulling together just cohort observational studies only. But to combine both, that may be inappropriate to some extent. Okay, this can also happen if you're combining poorly done or poorly designed studies. So for some reason, these poorly designed studies got published. So again, regardless, you still have to review all these individual studies and appraise them and judge for yourself whether they are appropriate to include in your meta-analysis or not. Okay, and of course, this happens when there's serious publication bias that exists. Okay, I'll be talking about a very common way of finding out if finding out mathematically if there's publication bias going on. So what happens now if we do what we're not supposed to do? Okay, so this actually introduces a huge amount of bias in your meta-analysis, and the results become seriously misleading. And if for some miraculous reason your meta-analysis gets published, this could actually send ripple effects to the public because you actually managed to publish misleading results, and this could potentially result in some harm. Okay, if you're not careful in terms of critically appraising and combining the studies that you intend to combine in your meta-analysis or systematic review. Now, in order to remember not to combine studies that are not supposed to be combined, think of this phrase or think of this mnemonic, GIGO. It stands for garbage in, garbage out, meaning a meta-analysis is only as good as the studies that were included. So if you've actually included inappropriately designed studies to, if you included inappropriately designed studies to combine in a meta-analysis, that does not magically make your meta-analysis, or that does not magically make the results better. Okay, so it often turns out that the resultant meta-analysis from the combination of poorly designed studies in itself also becomes a poor meta-analysis. Okay, so you actually have a bias that you can have a certain amount of bias that gets introduced because of that. Okay, so this usually involves a tendency of a measurement process to over or underestimate the treatment effect. Okay, and of course, this leads to misleading results, and you don't want to publish misleading results because this could send ripple effects, uh, wherein clinicians might uh, heed your misleading results, and this could actually lead to actual harm or actual patient harm. So again, be careful in be careful in how you combine your different studies that you retrieve from the database. And of course, you can always consult your research advisor for this, right? Now, perhaps the next question would be, why perform a systematic review and meta-analysis? First and foremost, you want to increase the statistical power of the overall studies. Okay, so what do we mean by statistical power? Statistical power of a study means that that particular study or experiment is able to detect a difference between two groups that they're comparing, when in the true state of affairs, there really is a difference that exists between the two groups. So your study was able to detect that difference. Okay, a study has poor statistical power if that study was unable to detect the difference that actually exists between the two groups that you're comparing. Okay, now for that matter, very often the RCTs that you're combining have small sample sizes. Okay, and because of the small sample size, they were unable to detect any effects between the two groups they're trying to compare. Okay, so and sometimes those effects are too small to detect by studies that have small sample size. Okay, now if you combine all these small studies together and increase or inflate the sample size by pooling them together, then there's a higher chance of detecting the effect or the difference that exists between the two groups that you're comparing in terms of response to treatment. Okay, all right. The next would be to improve precision. So again, it goes the same way as with increasing your sample size. Increasing your sample size also makes your estimates more precise, right? So it decreases the margin of uncertainty. Okay, so the estimation of an intervention effect can be improved when it is based on more information, and by that it's reflected by uh, more participants included, i.e., the sample size has increased. Okay, I'll show you an illustrative example in the next slide. Okay, so this figure here is what we will define later as a forest plot. So forest, so gubat in Tagalog. Okay, so that's called a forest plot. And so the dark dot represents the point estimate, while the horizontal line that crosses through that dot for each study listed here is what's called is what represents your confidence interval. Okay, so look at the first column in look at the first column or the first forest plot on the left. Okay, so above it you read individual study risk ratios and 95% confidence intervals, and you see listed in the far left the uh, um, first author, last name, and the year the study was published, and the sample size, okay, the small letter n, right? So, and then these are the different estimates that they were able to attain with their individual studies. And now take note of the column on the right, the forest plot on the right, which has a heading cumulative risk ratios and 95% confidence intervals. Okay, so we started off with fielding. So we have this point estimate and 95% confidence intervals. Then we bit by bit add the next study to this, and you see in the column that says small letter n that the sample size increases as we go down, But notice the width of the confidence interval. You see that as we gain more sample size, the confidence interval narrows. Okay, I hope you notice that as we go down the second forest plot here on the right. Okay, so the narrower your confidence interval is, it means that your study is more precise. There's actually lesser chances for, or not chances, but rather lesser margins for error, lesser variability. So it's more precise. It's the possible values to describe a particular estimate is much nearer to the point estimate. So there's lesser variability in the results because of the narrower confidence intervals. Okay, so hopefully that was clear. Okay, what could be other reasons why we perform SRMAs? Of course, obviously, to settle the controversies that arise from studies that have conflicting results. Okay, so we perform that to be able to so to say, once and for all, settle this controversy, although this may not always be the case in some instances. Okay. You also want to see if the effect size is consistent across the body of data. You want to see if the point estimates of each study are consistently on the side of benefit or on the side of harm. Are they on the side of uh, treatment being favored, or are they on the side of placebo being favored in the forest plot? Okay, so that's one way to find out. You also want to estimate the effect size as accurately as possible. Okay, so the larger your sample size is, the more robust the statistical power is. Okay, and so that is you want to make sure that your overall meta-analysis is robust or robust across the kinds of studies included. Okay. Okay, so as I mentioned earlier on in this video lecture, my approach here is to show you the different steps in performing, or the different basic steps in performing an SRMA, or a systematic review, or meta-analysis. Okay, if you want more details on how to do that, I prompt you to check out what's called the PRISMA checklist. Okay, so PRISMA here is what consort is to RCTs. Okay, so I'll be providing the website for the PRISMA checklist later on. But we'll go through these different steps one by one, or more accurately, we'll go through the different steps three at a time. So we'll be combining the first three steps, then the next three steps, and the last three steps. Okay, so we'll first start off with the first group of steps. Okay, so planning your SRMA involves the first three steps in this list. Okay, so we'll go through them one by one. Okay, so we've already been going on and on about formulating research questions ad nauseum already. So, but unfortunately, that's the first point where we start off with the whole research process. That is to formulate an appropriate research question. In this case, you make use of the PICO format, right? Because SRMAs, or meta-analyses for that matter, very commonly involve combining RCTs. But you can also do meta-analyses that combine different observational cohort studies, for instance, or different cross-sectional studies. That is also possible. Okay, but bottom line is everything research related always starts off with formulating the appropriate research question. Okay, there's no escape from that. Okay, so the question must be clearly focused. Okay, as has always been discussed, or always been mentioned about research questions. And it's for which literature is available and is of some importance or relevance, at least in a greater picture. Because why else would you perform this study if it's not societally relevant? Okay. Now, these studies should present data that can be combined. Okay, so very important when it comes to meta-analyses. So I've been discussing that quite a few times previously. You have to combine apples with apples, oranges with oranges, as much as possible, not combine apples with oranges, okay, in a matter of speaking, right? Okay, so again, allow me to give a couple of examples of research questions which can be appropriate to use for meta-analyses. Okay, so the first one would be, among individuals with cardiovascular risk factors, would high-dose statins offer better protection against cardiovascular events or death than standard dose statins? So following the PICO format, the P here would be individuals with cardiovascular risk factors. The intervention being evaluated would be high-dose statins, comparator being standard dose statins, and the outcome of interest would be occurrence of cardiovascular events or death. Okay, so here's another example. Among patients who suffered from acute STEMI, would receiving streptokinase within 3 hours of STEMI onset be protective against mortality in the short term? Okay, so again, following the PICO format, the P would be patients who are suffering from acute STEMI. The intervention that is being evaluated here is administration of streptokinase within the first 3 hours after the onset of STEMI, the comparator being not receiving streptokinase, and the outcome is occurrence of death. Okay, so mortality in the short term, right? So hopefully that makes it clear. Okay, so as with RCTs, as soon as you have your research question drafted, then you can now start writing up your protocol. So I'm not going to go through that to the immediate details anymore because uh, we've already gone through that in the previous video involving RCTs. So we can just pause this video for a while to read the information that is indicated here in this slide. Now, one thing that is different from RCTs is that with SRMAs, it is best that you register them uh, or inform or register or input your protocol in a registry just to inform that you are going to perform such an SRMA. Now, the reason for doing this is we want to try to avoid any unintended duplication or redundancy of SRMAs. Okay, so for instance, a group of researchers decide to perform an SRMA on a particular topic. They register it so that any other researcher group would not do the same thing because there's already a group that's working on doing a meta-analysis on this particular topic. Okay, although that really should not be a deterrent, you can still be able to perform another meta-analysis on the same topic, but you may perhaps need to change a bit your eligibility criteria. You might want to look at a different outcome you want to measure or look at different sets of comparators for that matter. Okay. Okay, so here are the websites of the registries where you can register your protocol for your SRMA. Okay, so you can pause this video to take note of the different web pages or web addresses, and then you can visit them on your leisurely time just to check out how things are, what type of information they're asking for the protocol for your SRMA, and so on and so forth. Okay. Okay, so the next step in planning your SRMA is to define your eligibility criteria. So pretty much the same way as with RCTs, except that with RCTs, you're applying the eligibility criteria on the individual study participants. With systematic reviews and meta-analyses, you are applying the eligibility criteria on the individual research papers that you want to include in your SRMA. Okay, so again, just to define, so your eligibility criteria should guide you as to which studies you should select or include and which you should exclude from your SRMA. Your eligibility criteria should first and foremost be guided by your research question and objectives. Okay, so that goes without saying, right? It also should be guided by the population of interest. Of course, that involves any geographical location or setting. Okay, which outcomes are you planning? Which outcomes are you planning to focus on? Okay, maybe you just want to limit to studies that make use of death as an outcome, nothing else. So again, it's up to you. As a researcher, you may use different outcomes, maybe occurrence of disability or recurrence or metastases. So there are many different outcomes to choose from as long as the data is published and is out there that you can retrieve. Of course, it's also guided by the study design. So you may choose to just include all RCTs and not observational cohorts, or you may just want to pool different observational cohorts, not RCTs. Again, it all depends on you as a researcher. Okay, perhaps you only want to focus on a certain way the methodology or the methods were performed. Okay, so again, it goes without saying you have to read the individual studies that you retrieve from the database. Okay, and perhaps you might want to decide on just focusing on papers that analyze the data in a certain way. Okay, maybe you just want to focus on studies that measure the effect size in terms of risk ratio and not odds ratio, and so on and so forth. Okay, now it's very important to do this because poorly defined criteria can severely impact the usefulness, applicability, and conclusiveness of your SRMA. So it's basically similar to combining studies that should not be combined. Okay, so it gives you misleading results. Okay, it can strongly affect the validity of your results of your SRMA, right? Okay, so here's a snapshot of the eligibility criteria of one example SRMA, which I got from Virginia Tech University Library. Right, so you can pause this video just to check out the different details that the researchers are looking for as far as eligibility of the studies they want to include in their SRMA are concerned. Right. Now, again, as always, if you do plan to go ahead and do an SRMA for your research project, by all means, please be in close communication with your advisor so your research advisor or preceptor can guide you through the process. All right, now to end this section on the steps in meta-analysis, uh, again, it's important to consider the directness of evidence to the target population that you have, at least as far as your research question is concerned. So, can the findings of the review that you will make be applied to the patients uh, who belong to your target population that you have identified in your research question? Okay, so here are a few examples or instances. Of course, again, reiterating the importance of forming or formulating a proper eligibility criteria or inclusion exclusion criteria. Okay, because if you only focus on combining studies that only studied men, of course, you cannot apply the results of this meta-analysis or SRMA on females, obviously. Now, if you only limit the individual studies that you want to combine involving only diabetics, of course, you cannot be able to use the pooled estimates to make generalizations about another population, i.e., that population that does not involve diabetics. Okay, so I think that's stating the obvious there, right? Okay, so the next three steps in this list involve the data search and collection aspect or part of the whole SRMA process. Okay, well, again, as with previous, we will go through them one by one. Okay, so it goes without saying that the literature search that you have to perform for a meta-analysis or a systematic review has to be comprehensive. And don't forget as well which time points you want to set your search to. Like, are you interested in articles dating from year 2000 onwards or whatnot? Again, you decide as researcher what your time points are. Okay, so you've already discussed this in a previous video about literature search. I'll just go through this slide pretty quickly. So whenever you do searches, of course, you have to type as well synonyms or related words, or words that are closely related to your key your key search words, right? Like for instance, dizziness might actually be related, at least as far as your meta-analysis is concerned. You think it you think words such as lightheadedness and vertigo might have been used in place of dizziness in certain studies. As for diabetes, okay, maybe the terms insulin dependent or non-insulin dependent might have been used. Of course, some researches or some papers would also use the terms type 1 or type 2, right? So you have to be wary about such synonyms or related words, okay? And you also need to use wildcards to be able to expand your search. Okay, like these two examples here. So, first example made use of asterisk, and you situate it at the end of the word. So it's basically a truncation. So uh, what the search database will interpret this as would be it would search for words that have other letters beyond the asterisk that was placed in the end of this key search word, right? And the other example made use of the question mark wildcard. Okay, so women, uh, WOM question mark N could either mean woman or women, right? And you also have to be aware of how English and British English, American English and British English are spelled. Okay, so here are a few examples. So I already touched on the use of Boolean operators. So in a previous video, it was defined what and, or, and not mean. Okay, and of course you have to search different databases, not just PubMed, right? So I'll just show you a list of different databases in the next slide, right? And not only that, for of the papers that you were able to retrieve, you also have to look at the bibliographies as well, if there are any related articles indicated there in the bibliography or references, which could actually perhaps satisfy the eligibility criteria of the papers that you want to include in your systematic review and meta-analysis. Right? Okay, so here are different places where you can actually search for your literature. You can just pause the video and go through them. All right. It's pretty self-explanatory. There's one thing though that I need to point out. So notice that I actually place an asterisk beside Google Scholar. It's actually not recommended to add Google Scholar as one of your databases, especially if you want your meta-analysis to be published. It's because the search results that are being returned by Google Scholar are very dependent on your location on the globe. Okay, and since it's essential that there's reproducibility of the search results of your meta-analysis, because you also have to publish your keywords, okay, and your search strategy in your methodology. If somebody else did or performed the same search using the same keywords, that person should more or less get the same uh, search results as you did for your meta-analysis. Unfortunately, Google Scholar is not so consistent with the search results that it returns back to you, because it's very dependent on where you are on the globe, right? Okay, so now that you've done your literature search and you now have retrieved the articles that you need for your SRMA, the next thing that you have to do is to evaluate the quality of evidence contained within each article, right? So basically, this involves estimating the risk of bias that may be present in the methodology or what have you in each individual paper that you will potentially include in your SRMA. Now, the Cochrane collaboration actually has a risk of bias tool that covers these following domains. So it evaluates for any presence of randomization that was done during the course of the trial. How was allocation performed? Was there any concealment that was done? Was blinding done properly? Uh, Was there any potential for attrition bias? Was there actually selective outcome reporting in the results in each paper that you've retrieved? And you also need to assess for the possibility of other biases, right? So this tool allows you to mark um, the risk of bias three ways. So green, it's color coded actually. So green if there's a low risk of bias. Unclear, then you make use of yellow. And if the risk of bias is high, then you make use of the red color to mark such paper, right? And you do that for each of the domains. I'll actually show you a figure of that shows the different domains and how each paper was evaluated making use of this color coding, right? Okay, so here is the Cochrane Collaborations tool for assessing the risk of bias. So I already showed you the different domains in the previous slide. So you can pause this video and spend more time to read what's written in this particular table, okay? Because it really is just a sort of a repetition from previous. But do take your time to read more into this so you will be more familiarized as to which domains are being evaluated in terms of risk of bias, right, using this tool. Okay, so here are a couple of figures that show you how the Cochrane collaboration tool can be reported as a graphic, right, or as a figure. So the rows here represent each study and the columns represent each domain that is being evaluated for risk of bias. And you can see the color coding that was done. So you'll notice as well that the green color has a plus or a positive or a plus symbol in it, meaning that there's a low risk of bias as far as for this paper or for these papers as far as each domain is concerned. As I mentioned earlier, yellow represents unclear bias, and there's a question mark. In some instances, this coding includes a question mark included inside the yellow circle. And as for high risk of bias, of course, it's color coded red with a negative sign in it. Right? Now, the graphics that I showed you in the previous slide can actually be generated by RevMan after the analysis of your data. Now, another graphic that RevMan can generate for you is this one that you see here in this slide. So basically, it takes each domain and it summarizes the percentage of studies that have low risk of bias, unclear risk of bias, or high risk of bias. So this is actually an example of it. Okay. Okay, so happening alongside evaluation of the quality of evidence is the process of data extraction. Okay, so you start extracting the data that you will need to pool for your meta-analysis or systematic review. Okay, now systematic reviews and or meta-analyses require at least two different investigators extracting the data independently. So they're working on extracting the data from the retrieved articles independently, right? So the extracted data are then reviewed by these two investigators, at least two investigators. There can be three or more, but the requirement is there has to be at least two for meta-analysis or systematic review, right? So keep that in mind. So they do the data extraction independently, and afterwards, they at some point meet and they compare notes. Now, if there are differences in opinion between the investigators, they resolve it by means of debate. And in case they come to a deadlock, then they will need the help of a third reviewer for consultation so that they can arrive at a consensus. If there are any conflicts in terms of which paper to include or exclude, was there any problems with data extraction and whatnot. Okay. Okay, so the last chunk that has to be done with SRMAs would involve the results and analysis, and this actually encompasses the last three steps I have here listed in this slide. Right? Okay, so what exactly do we do here in this part that involves results and analysis? Okay, so we want, of course, first and foremost, to detect if there it is a treatment effect that is present. Okay, is a treatment beneficial or harmful? And not only that, we also want to know the size of that effect. Is the benefit or harm for that matter substantial or just trivial? Okay, and next, we also want to evaluate the homogeneity of effects among studies. And then we look at the I-squared statistic for that, which I'll be discussing later. What this means is it is at this part where the whole concept of combining apples with apples or oranges with oranges comes in. So, is there homogeneity or heterogeneity among studies in terms of the estimates that were derived? Okay, so there's actually a mathematical way of finding it out. So the software will do that for you. Okay. And afterwards, you have to evaluate for the strength of evidence that is contained within each paper that you'll be including potentially in your SRMA, right? Now, here's a website that you can check out to see the different free software that's available that you can use for your results analysis for your meta-analysis, right? Although the most frequently used one is RevMan. And I provided the website for you where you can download it. So you can actually go to the Cochrane collaboration website for that. I also provide also providing you with the website where you can actually have tutorials for Revman because how to use Revman is actually beyond the scope of this video lecture. Now, you also have other software that you can use, at least the ones that I'm familiar with would be Stata and SPSS. These are not free, however, and you may need the help of a statistician for this. Right? Now, remember I gave you two examples of research questions for meta-analysis earlier on, some slides back. Now, we'll make use of the first research question as an illustrative example for a meta-analysis. Okay, this we'll be making use of statin clinical trials. Okay, so an SRMA of cardiovascular clinical trials was actually designed where patients were randomized to receive either a standard dose or high dose of statins, if you could still remember the research question that was posed earlier. The outcome of the studies were the proportion of patients who had cardiovascular events or who died, right? And then the effect size that was used in this case was the risk ratio. Okay, I'll be showing you the results later. Now, according to the eligibility criteria of the researchers who wanted to do this meta-analysis, they ended up including just 4 papers. Uh, and you'll notice that very commonly in a lot of RCTs are actually given catchy names. They're often mnemonics or abbreviations that describe what is being done in the trial. Okay, so you have 4 RCTs that were included in this meta-analysis: the Prove It trial, the A to Z trial, the TNT trial, and the Ideal trial. And you can see with the subsequent columns the number of events that occurred in the high dose group. So when we say the number of events, the events in question here would be the cardiovascular events or death. And you also have in the next column the number of patients you have overall for each trial in the high dose group. Now, that would be for the high dose treatment arm. So you also have similar columns for the standard dose treatment arm. So the next column involves the number of participants in the standard group who had the event during the trial. And for each study, you also have the total number of patients who got randomized in the standard dose group. Okay, so you can pause the video to take note of the numbers here, right? Okay, so let's say Revman was used to analyze the data. So the data that was presented in the previous slide was inputted by the researchers into Revman. So after instructing Revman to analyze the data, it gives you an output that looks something like this, right? So this is the usual output or graphic that you will see in meta-analyses. So let's look at the different parts of this figure here. So this part is what's called the forest plot. So I already mentioned what the forest plot is earlier on in this video lecture. So this column here shows you the effect sizes for each study. So you have the point estimate, okay, and you also have the 95% confidence intervals that are included in brackets. I will be talking also about the weights assigned, weights assigned to each study, okay. So this is actually dependent on the sample size of that particular study, right? Usually. And we also have this particular piece of data here. This is actually the summary effect or the pooled effect. After taking into consideration the point estimates and confidence intervals of each study, as well as the weights assigned to the effect size of each study. And there's also another important part, this part here. This actually gives you an idea of how heterogeneous or how homogeneous the different studies that you included in your SRMA are. Okay, and you can see here the I-squared statistic. We'll be talking about the I-squared statistic in a bit. Okay, so at this point, you already know what or how a forest plot looks like. So from the image that I showed in the previous slide, so you see there are squares and horizontal lines running through each square, and there'll be one for each study. And at the end, you have a pooled estimate that is represented by a diamond. You'll notice that the forest plot also can be divided into two halves. So there'll be one side that shows you whether the data prefers or favors the treatment, and the other side which tells you if the data available favors the placebo. Okay. So overall, the forest plot serves as a visual or graphic representation of the results of your meta-analysis, right? So here in the forest plot, each study, as well as the combined or pooled effect, is depicted as a point estimate bounded by its confidence interval. So you will notice in the image that I gave in the previous slide, so for each study, there's a point estimate represented by a square, and each square actually has a horizontal line that runs through it. That horizontal line represents your confidence interval, which we usually default to 95%, okay, the 95% confidence interval. Now, the forest plot shows if the overall or pooled effect is based on many studies or a few. In the example that I gave on statins, there were actually 4 RCTs that were included. Okay? It will also show you studies that are precise or imprecise. And we actually base this on the confidence interval. How wide or how narrow are the confidence intervals of each study? Okay, so if you could still remember from earlier on, if the sample size increases, you notice the confidence intervals narrow, right? So the narrower the confidence interval, the more precise the study is, okay? Because there's actually lesser chance for variation or possibility of different values besides a point estimate that was given. Now, forest plots also show you whether the effects for all studies tend to line up in a row or not. So we refer to that as a direction of the effect. Now, do all or most of the point estimates lie on one side of the forest plot, i.e. the side that favors treatment, or are they consistently on the other side, i.e. the side that favors the placebo? Okay. Now, your forest plot also shows whether the studies that you've included vary substantially from one study to the next. And that is where your homogeneity or heterogeneity principle comes in. Okay. Now, I mentioned earlier that you could actually mathematically estimate or evaluate your the heterogeneity by means or by use of the I-squared statistic. But you could also sort of eyeball from the forest plot to get an idea whether the different studies are heterogeneous or homogeneous, okay? And you base that on how the point estimates and confidence intervals line up for each study. Okay, so I'll show you a very quick way on roughly estimating whether a meta-analysis has studies that are heterogeneous or homogeneous with respect to each other. Okay. Okay, so let me now leave the forest plot for a bit and talk about these so-called effect measures, which are used to represent the effect sizes that are being reported by each study. So if you could go back to the figure that I gave, the effect sizes would be the numbers that are in the column right beside the forest plot. Okay. Now, the type of effect measure to use depends on the type of variable your outcome variable is. Okay, so there are only two possibilities. So first, is the outcome a categorical outcome, or more precisely, is it a dichotomous outcome? Meaning, uh, there are only two possibilities for each participant in terms of outcome, whether the participant attained the outcome or they did not at the end of the RCT. Now, if the outcome is categorical in nature or dichotomous in nature, then we make use of these effect measures: risk ratio, risk difference, and odds ratio or odds ratio. Okay, so Revman could actually be able to switch from one outcome or one effect measure to the other. Now, what if your outcome is continuous in nature? So, what would be examples of continuous variables? So, when we say continuous variables, these variables have an infinite number of possible values. So, one example would be temperature. So, you can actually have 36.5, 36.49, 36.48. So, there are many possible values that you can assign for that particular variable. Okay. Now, in case your outcome is of that nature, then you have to make use of either the mean difference or the standardized mean difference. Okay, because you want to see uh, the differences in means of the outcome between the two treatment groups, right? Now, as I mentioned earlier, the effect measure or the effect sizes are represented by a square, so that would be your point estimate, with the location of the square representing both the direction and magnitude of the effect. Okay, so for instance, is the square on the side that favors a treatment, or is it on the side that favors the placebo? And how far is that square from the midline or the null value? Okay, so the further away it is, the greater the magnitude of that effect is. Okay. And as I mentioned earlier, each square or each point estimate is bounded by a confidence interval. That would be the horizontal line that crosses each square. Okay, so you can have you have one square for each study that was included. Okay, so as I mentioned earlier, the confidence interval reflects the precision with which the effect size has been estimated in that study. Okay, so the wider the confidence interval, the more imprecise the study is. The narrower it is, the more precise it is. And this is very dependent or mainly dependent on the sample size. The more study participants you have in the study, the narrower the confidence intervals tend to be. Okay. Now, the confidence interval also identifies whether the effect measure is statistically significant or not. And I will show you later on how to know whether each effect measure or each effect size has statistical significance or not. Okay. Okay, so let's look at a couple more examples of Revman outputs. Okay, so here's one output that involves an outcome variable that is continuous in nature. So in this case, the researchers made use of mean difference as the effect measure. And you have the effect sizes listed here, right? And you have the pooled effect size overall. And you have the forest plot beside it. So you notice again that the forest plot has two halves. So one half, one of the left one rather, is usually one that favors the investigational treatment, while the right side would usually represent the one that represents the control. Okay, and again, you have the different point estimates and confidence intervals for each study here, and you have the pooled effect that's represented by the black diamond down below. Okay, so now here's another example, but this time we're still making use of, this is still actually involving a continuous variable, but this time they made use of standard mean difference. Okay, so usually the standard mean difference is used if different studies actually have different units that were used to measure their outcome. Unlike if the studies actually have uniform units that were used for their continuous variable outcome, then you can make use of the mean difference. But if the outcomes, even though it's the same outcome, but the outcome is being measured using different units, then we could actually be able to standardize uh, the whole thing by making use of standard mean difference instead. Okay, so there are actually two possibilities when you're dealing with continuous outcome variables, right? Okay, so let's go back to the original SRMA that we made use as illustrative example, the one that involves high dose and standard dose statins. Okay, so if you're observant, you would know that the outcome variable is a categorical or dichotomous one. That is, whether the participant attained the cardiovascular event or not. Okay, and you'll notice from the Revman output that was presented a few slides ago that risk ratio or RR was used as the effect measure. Okay, you'll notice that it's strongest, that is, it's most distant from the center or the null value with the TNT study, and it's actually weakest with the ideal study. So it's weakest because the point estimate is nearest to the midline or the null value midline. Okay. Now the effect size for each study that was included in this SRMA falls to the left of the center. Okay, which actually tells us that there's benefit for the high dose group, or the high dose group is actually the one preferred. Okay, and you'll notice from the 95% confidence intervals, that is for the ideal study, that one is narrower than that of the prove it study, reflecting that the ideal study actually has greater precision, right? So the narrower the confidence interval, the greater the precision, and this is usually dependent, or is mainly dependent on the sample size of the study. Now, overall, only prove it was statistically significant, and let's try to investigate why that is. Okay, so let's now go back to the Revman output for our statin SRMA. So the pending question is, why is the TNT study, or the TNT RCT, the only RCT that is statistically significant or has the statistically significant effect size? Now take note of the four studies point estimate and confidence intervals. Do you notice anything unusual there? So I'll give you a few seconds to figure that out. You can pause this video if you need. And if you know the answer already, so we can uh, unpause the video so we can move on to the next slide. Now, if your answer is that the confidence interval of the TNT study did not cross the null value midline, then you are correct. Okay, so here are some illustrations of point estimates and confidence intervals. If the confidence interval did not overlap the midline, which is the null value, 1.04 ratios and 0.4 mean differences, then that study has statistically significant results, right? Okay, so let's very briefly touch on study weights. Now, the weight is assigned to a study, and it's usually the software that does that for you. It's assigned to a study, and it's related to the study's precision, and by extension, the sample size, because, of course, precision is dependent on the study's sample size. Okay, so again, the larger the sample size of that RCT or study, you'd expect the results to be more precise. Okay, so the weight assigned is related to the study's precision. and by extension the sample size, okay, which is actually in this sub-bullet here, right? Now, you will notice the study weights are reflected on or are reflected by the sizes of the squares in your forest plot. Okay, so the squares vary in size, reflecting the weight that is assigned to the corresponding study when computing the summary effect. Now, going back to our statin SRMA, you will notice that the TNT and ideal RCTs have relatively good precision, okay, and are thus assigned relatively high weights, as you can see from the sizes of their corresponding squares, and perhaps to some extent the width of the confidence intervals they have. Okay. Okay, so let's now move on to discussing the summary effect. So the summary effect basically embodies the whole goal of your SRMA. Okay, so because with pooling together of the estimates from your different RCTs, you effectively increase the total sample size, and with increasing the total sample size, you actually improve the precision. And this improved precision actually addresses the accuracy of the summary effect as an estimate of the true effect, which basically remains unknown. So the true effect is something that is the attribute of the entire population, but since we only have an estimate, we only have a sample size of that population, we can only get as near as an estimate of that true effect. And by increasing the precision of our study, the closer we get, uh, the closer our estimate gets to that so-called true effect. Okay. Now, the summary effect basically represents the weighted means of the individual effects, right? And RevMan actually gives you two options on how to get to your summary effect. So either you do it by using the fixed effects model or the random effects model. So there are actually some assumptions that are being made here. So uh, with the fixed effect model or fixed effects model, you assume that the studies share the same true effect size, while with the random effects model, you anticipate that the effect sizes vary from study to study. Okay, so now you don't really have to worry yourself so much behind the whole concept of what each effect model or what the fixed effects or the random effects model represent. Uh, what you probably should know is that researchers very often default to using the random effects model because we assume that because you can have high variation between studies, you would expect the true effect sizes being measured to vary from study to study. So we normally default to using the random effects model. It's too technical, but and for that matter, I don't really suggest that you belabor so much on understanding what the differences between these two models. Okay. Now the summary effect in the forest plot is represented by the diamond. Okay. The location of that diamond tells you what the effect size is. How far away is it from the how far or how near it is from the midline. Again, the farther away the estimate is from the midline, the the higher the magnitude, uh, and the closer it is to the midline, the weaker the strength is. Okay, and then the width of the diamond represents the precision. Okay, so you would notice that the width of the diamond is much narrower as compared to the confidence intervals of the individual studies. Right. Okay, so here in this slide, we have two Revman outputs, but they're actually from the same meta-analysis, except that the upper output made use of the fixed effects model, while the lower output made use of the random effects model. Take note that with the random effects model, the pooled effect or the diamond is generally wider than the fixed effects model, so it's something to keep in mind. Okay, and again, we generally default to random effects estimation because we cannot really anticipate beforehand for sure or for certain that um the true effects being estimated by each study would be the same. So it's hard to make that assumption. Okay, so we typically default to using the random effects estimation. Okay, we just instruct the RevMan to do random effects rather than fixed effects. Okay, so let's go back to our original illustrative example. That is the statin SRMA. So in this SRMA, the summary risk ratio is 0.85. So the way that you interpret it is whenever the risk ratio is below 1, you subtract the risk ratio from 1. So 1 minus 0.85, you get 0.15. So this means that the risk of cardiovascular events or death was 15% lower for patients assigned to the high dose statins than for patients assigned to the standard dose statin group. Okay? Now, if you go back to the forest plot, you notice that the diamond is centered at 0.85 and it extends from 0.79 to the 0.92 mark on the forest plot. And you can actually double check this by looking at the summary effect numbers beside it. Okay, so the this actually represents or tells us that the actual impact of the high dose statin group or giving high dose statins likely falls somewhere in that range. Okay, so basically with increased precision, as I said earlier, we get closer to the true effect, which is still largely unknown. Which is the most we can do is estimate it, but according to the studies that we were able to pull together in this meta-analysis, there is actually a benefit to taking high dose statins compared to standard dose statins among patients with cardiovascular risk to prevent cardiovascular events or death. Okay. Okay, so the last thing to talk about would be heterogeneity or homogeneity for that matter of the effect sizes of the different studies you included in your SRMA. So this measure assesses the dispersion of effect sizes from study to study and takes this dispersion into account when interpreting the data. Okay, now there are actually three possibilities in terms of study heterogeneity. First, you can have the effect sizes consistently on one side of the forest plot. Okay, so if that happens, it means that you have studies that have pretty consistent results. Okay, now if you have that kind of output or result with your SRMA, the next thing you have to do is to focus straight on the summary effect or the diamond, because this effect is actually robust already across the studies included. Now, it could also happen that there's some modest variation in terms of effect sizes, meaning you would have most point estimates in one side of the forest plot, and some would be a little bit scattered on the other side. Okay, so it's not exactly consistent as with the first possibility. Now, if you actually get this kind of output with the meta-analysis you're going to perform sometime in the future, maybe, uh, what you need to do is you might still need to report the summary effect, but note, however, that the true effect could be somewhat lower or higher than this value. Okay, so because of there's variation, yeah, you do have a summary effect, but keep at the back of your mind that because of the variation in effect sizes between studies, there could still be some uncertainty, some degree of uncertainty with your summary effect. Okay. And lastly, you can have the possibility wherein all of your studies have substantial variation, meaning there's low consistency between the effect sizes between the different studies involved. Now, when this actually happens with your SRMA that you perform, you shift away your attention from the summary effect because it's going to be unreliable anyway, and instead focus on the dispersion itself. What could be possible reasons for the heterogeneity? So you need to investigate that, and we will be touching on that a few slides from now. Okay. But first, let's look into ways in which heterogeneity can be reported numerically, okay, or can be tested numerically. So, heterogeneity can be tested using the chi-square test. Okay, so some of you might start getting nervous. Ooh, there's some mathematics involved here. There's some statistical measures involved here. Don't be nervous with this one. All you need to do is to just look at the p-value. If the p-value for that particular chi-square test, which is actually reported in the Revman output, if it's less than 0.05, it means that the effect sizes between studies are not consistent, i.e. there's high heterogeneity, okay, if the chi-square test turns out to be significant or have a low p-value. Now, the heterogeneity can also be assessed by means of this so-called I-squared statistic, okay? So this I-squared statistic indicates the percentage of variance or variability that is attributable to study heterogeneity. Now, a few slides from now, we'll be looking at possible reasons for heterogeneity. Okay, there are many reasons why studies that were combined together are heterogeneous. Okay, now if the I-squared is high, there are some suggested remedies. We will go through them later on. So just to name a couple, or just to name one possible way to address high heterogeneity, is you look at certain subgroups in your population. Maybe because, of course, the sample size or the sample that was pulled together is not exactly a homogeneous group most of the time. You can actually have certain subgroups within that sample that appear to maybe have a higher risk for the outcome, perhaps, that maybe perhaps they actually have a better response to the investigational treatment. We don't know. So that's actually something to look into. Okay. Or after you've already gone through the remedies, maybe you'll have to resign to the fact that maybe the studies that you combined should not have been combined in the first place, i.e., you were combining apples with oranges, as I've been talking about earlier in this video lecture. Okay. Okay, so now how do we interpret the I-square statistic? Now, there's actually a rule of thumb that is indicated in the Cochrane Handbook for Systematic Reviews of Interventions. And here are the rules of thumb. So if the I-squared is 30% to 60%, this may represent moderate heterogeneity. If it's 50% to 90%, this may represent substantial heterogeneity. If it's 75 to 100%, there's considerable heterogeneity. But take note that there's actually also substantial overlap between these ranges. So you can see that the 30 to 60 range overlaps with 50 to 90, overlaps with 75 to 100. So basically, there's no mutual exclusivity. Okay, I think I said that right. Now, so far, the rule of thumb that was presented by the Cochrane Handbook may not actually be too helpful after all at first blush. But perhaps for our purposes, let's just focus on this. Okay, if your I-squared is from 0% to 40%, it may not be that important unless you are interested in investigating, particularly if your I-squared is near 40%. Okay, so it's up to you as a researcher whether or not you want to look into subgroups or do meta-regression or all those other remedies that we'll be talking about later in case you have high I-squared. Okay, now Revman does not do this, but there are some statistical software that can report negative I-squared values. If that is the case, then it's actually automatically considered as 0%, right? Now, I did mention earlier that you could be able to sort of gauge the amount of heterogeneity there is by just eyeballing the forest plot. Now, let's take the output from above, output that's situated in the upper part of this slide. Now, if we were to run a vertical line down the components of the forest plot, and that vertical line intersects with most, if not all, of the confidence intervals, then that's one rough way of finding out that the studies are more or less homogeneous. not there's lesser heterogeneity. If you would check the I squared, if you would check the corresponding I squared, you see that it's 43%. So based on what we defined earlier, it may not be that bad of an amount of heterogeneity. However, let's look at the example below, the output below. You run a vertical line like so, and you see that there are two studies that whose confidence intervals do not intersect with that vertical line. If anything, the effect size of the study by Arici, 2009, seems to have a stronger magnitude or stronger effect because it's furthest away from the midline. And you have the study by Iogen, 2008, wherein the point estimate is actually on the other side of the forest plot, the other side of the null value. Now you can see just by looking at this that you'd expect heterogeneity in the studies. And true enough, look at the I squared. The corresponding I squared is 79%. Okay, so there's actually some substantial heterogeneity going on. Now let's go back to our illustrative example, the statins SRMA. So the test for heterogeneity yielded a p-value of 0.7428. So the chi-square test for heterogeneity had a p-value of 0.7428. So it's well above 0.05, meaning there's no statistical significance. So the way that you interpret this is the studies and their effect sizes are consistent, meaning they're not heterogeneous. Okay, and this is likewise reflected by the corresponding I squared that is 0%, right? Now, here's the burning question. What if you have high heterogeneity with your meta-analysis results? The next question you have to ask yourself is, why is there heterogeneity? Okay, so here would be, you would actually need to explore different possibilities why the heterogeneity of between studies is high. Now, one possibility could be the so-called statistical heterogeneity. There is actually different intervention effects or results. That's basically what it means. It could also mean clinical heterogeneity. Maybe the types of participants that were recruited for each RCT was actually quite different in terms of baseline characteristics or patient profile. It's possible, okay? Or maybe, even though the name of the drug is the same, maybe the method in which the intervention was administered was different between studies. And maybe the outcomes that were measured or the way the outcomes were ascertained were different across different studies. So that's another possibility. Now, a third possibility is there could be what's called methodological heterogeneity. So it may be because of differences in study designs or differences in the risks of bias. Okay. Now, here are perhaps some remedies you can do initially when you see that your heterogeneity is high and you need to look for explanations as to why heterogeneity is high. First and foremost, go back to the drawing board. Maybe you might have made a mistake in encoding or inputting the data into RevMan. So just double check that first and foremost, because a lot of times that might just be where the problem lies. Next is you can actually switch between random effects and fixed effects model or modeling. Okay. Now, this is only for heterogeneity that cannot be explained because it is due to chance, right? So you can try exploring that either way. Next, you might need to reconsider the effect measure that you're using. Maybe risk difference might not exactly be the best effect measure to use. Maybe you can try switching or asking RevMan to switch from risk difference to risk ratio or odds ratio. Okay, so maybe you could actually perhaps get different heterogeneity values in doing so. Now, I do have a few more measures you can take. They're a bit technical, so you may need a statistician's help for that. But at the end of the day, if after you've exhausted all remedies and the heterogeneity still remains unexplained, then maybe you should just resign to the fact that maybe the studies you have included in your SRMA should not have been pooled or combined in the first place. Again, I allude to the so-called uh, um, apples and oranges being grouped together. Now, if that would be the case, instead of performing the mathematical portion of your SRMA, i.e., your meta analysis, you should just settle on doing a systematic review instead of the full SRMA, and you report your results in narrative form. Okay. Okay, so I mentioned earlier about sensitivity analysis as one measure of investigating heterogeneity. So, what does that mean? Now, for instance, so you already have the list of studies that you would include following your eligibility criteria, yet there might be one or two of them that you might be questioning the methodology, for instance, that maybe that might be the one driving the heterogeneity. You could actually instruct Revman to uncheck the estimates of those studies or the contributions to those studies, and you run the forest plot again and see if the I squared would change. So that's one way of doing so. Okay, so you try excluding some studies which you've already included initially, yet a little bit questionable with the methodology. So after rethinking, okay, let's try to see what the I squared would be if we exclude those studies. So you can try doing that. Now, there's another thing that's called subgroup analysis. Okay, so what this means is you split all participants in your sample into subgroups, and these subgroups depend on characteristics, demographics, risk factors, and then afterwards, once you've separated them into subgroups of interest, you repeat the analysis in each subgroup, and then you compare the results between these subgroups. So, what could be examples of such subgroups? So there you have male, female, you have smoker, non-smoker. You can have age groups as subgroups as well. You can have comorbidities like who are hypertensive and who are non-hypertensive. You can have also it could also be in terms of dosage of a certain medication. Could be high versus low dose. Okay. Now you notice that these variables are categorical. Okay, so sex has only two categories or two possible answers, male or female. So is smoking status, smoker, non-smoker. Age group, it could be three age groups of interest, we don't know. Hypertension, whether you have it or not. Dose, high dose, low dose. So again, these are all categorical variables. Okay, so all in all, subgroup analysis allows for investigation of the influence of a particular categorical characteristic. That is, I'm referring to the ones above. Okay, so maybe if we actually separated those groups according to those, if we actually separated our participants into those subgroups, maybe this could actually correct the high I squared for all we know, because it might be sex that could be driving the heterogeneity. Maybe the estimates for male might be different for female. It's always possible. The estimates for smokers might be different for non-smokers, and so on and so forth. Okay. Now, actually, there's another analysis that involves the influence of a continuous characteristic, and we call that meta-regression, which we'll get to later on. Okay. Okay, so here's an example wherein we did subgroup analysis. So the subgroups in this case were the categories of sex, so males and females. So they actually separated the studies according to the population that they studied. So basically, there were studies that exclusively studied males, and there were studies that exclusively studied females. So they separated those studies, they grouped them together according to the subgroups. They did their own estimates. They have separate forest plots, as you can see, and they have separate pooled estimates or separate diamonds. Okay, and then originally, the I squared when the all of these studies were pooled together was quite high. So therefore, there was actually initially significant heterogeneity. Now, after separating, you see that the I squares for both subgroups are 0%. Notice as well that the magnitude of effect of intervention A appears to be greater among males than females. As you can see, the distance of the diamond from the middle line, the null value of 1.0, is further among males than among females. Now, you'll notice another measure here. Okay, this actually pertains to the two pooled estimates, or the two diamonds. So basically, this last measure here does not pertain to all of the studies. It just pertains to the two pooled estimates, or the two diamonds. What it says here is the chi-square test showed a p-value of less than 0.05 with a pretty high I-squared. So this does not say anything about the heterogeneity of all of the studies with respect to each other. As I said, this measure here, as you can see, it says test for subgroup differences. It just pertains to the two diamonds. So basically what it means is the pooled estimates are significantly different from each other. Okay, as noted by the p-value that is significant and the high I-squared, which shows that these two are quite different from each other. Meaning, after doing subgroup analysis, the researchers were able to uncover that sex actually plays a role in terms of response to intervention A, with the magnitude of response apparently greater among males than among females. Okay, so here's another situation which is similar from the first example. They had the same subgroups, sex, so they separated they grouped the studies according to categories of sex, males and females. Okay, because same situation as the previous one. When they pulled all of the studies together, the I-squared was quite high. There was significant heterogeneity. So after doing subgroup analyses, you'll notice again that the I-squared statistics are down to 0% for both pooled estimates. Okay. Now notice this time that the I-squared pertaining to the two diamonds, or the two pooled estimates, is much lower than the previous one, which is around 75%. And the p-value is now above 0.05. So basically, this test for subgroup differences tells us that there's no statistically significant difference between the pooled estimates among males and females. And on top of that, notice that both diamonds overlap the 1.0 midline. And basically that tells us that in terms of treatment effect for both sexes, there's no difference between intervention A and intervention B. Okay, so that's what it means. Okay, so recall from a few slides back that I mentioned meta-regression as another method for investigating heterogeneity if the heterogeneity is significant. Okay, so think of meta-regression as an extension of subgroup analysis. Now recall that subgroup analysis allows the investigation of the influence of a categorical characteristic on the effect measure. Okay, so and by that we looked at a few examples. I gave a couple of examples wherein the subgroups are sex, and I showed you separation of the effect measures depending on the subgroup that was investigated. And I also gave a couple more examples of other subgroups. We talked about smokers, non-smokers, etc. Now, with meta-regression allows the investigation of the influence of a continuous characteristic on the effect measure, right? So earlier on, I gave examples of continuous variables, I believe, in the RCT lecture. Okay, so you can just review what they are. Now, one thing about meta-regression is you generally should not consider doing it when the number of studies that you are able to retrieve and pool are less than 10. If it's more than 10, it's always good to look into heterogeneity from the meta-regression lens. Okay, so I'll give one example of a meta-regression in the next slide. Okay, so this is how a meta-regression looks like. So it looks pretty intimidating, but allow me to walk you through this. Now, this was actually from a meta-analysis that looked at two blood pressure medications or compared two blood pressure medications. And this was in terms of the effect measure risk difference or risk reduction in terms of CVD or cardiovascular disease. However, there was a high heterogeneity in terms of the studies that were pulled together. So there was high heterogeneity between the studies that were included in this meta-analysis. And the researchers identified beforehand that in case heterogeneity was high, that they would look into differences in response to the interventions in terms of systolic blood pressure reduction. So what they did now was they plotted the percentage risk reduction in major cardiovascular disease events against the difference in achieved systolic blood pressure between treatment arms. So the circles that you see here refer to the individual studies, and then the larger the circle, this corresponds to the weight that was assigned to them during the analysis portion. And as you can see, there appears to be a linear trend. And after the straight line or regression line was fitted, it seems like the relationship that appears to be present here, which explains the heterogeneity between studies, was that the higher the reduction in systolic blood pressure, or the that is a response basically. So basically, the higher the reduction in systolic blood pressure, the greater the percent risk reduction in major cardiovascular disease. Okay, so what it all goes down to is basic linear algebra, right? Okay, so let's now move on to level of evidence assessment. Now, I talked about the Cochrane collaboration tool for assessing the risk of bias earlier. Now, this time, in this part of the whole meta-analysis process, we're done with assessment of the risk of bias. So we've already done that earlier on. What we're trying to assess for now, this time, is the quality of evidence that is contained within each individual study. And the tool that we would normally use, or what we generally use for that, would be the grading of recommendations, assessment, development, and evaluation, abbreviated as GRADE. So in this case, quality is evaluated, or quality of the evidence contained in each of the individual papers is evaluated on the basis of the study limitations, inaccuracies, incompleteness of outcome data, indirectness of evidence, and risk of publication bias. Okay, so again, it stresses the importance that you have to read each and every paper that you would include in your meta-analysis. Okay? And this tool is also used to determine the strength of recommendations. And the quality using this tool can be classified as either high, moderate, low, or very low. Now, here's a website, so you can check it out to see more details about GRADE and its other indications, right? Okay, so this table here shows you the 4 levels of evidence quality as indicated in the GRADE tool, and what each what each means. Now, I mentioned earlier about the so-called true effect and estimated effect. Okay, now when we say true effect, that is the effect that you would be able to measure if you're able to study each and every single person of the population. But for obvious reasons, we cannot be able to study or measure every single person in this vast population. So what we can do instead, to make it much easier and more feasible, is we get a representative sample from that population. And it is from this sample where we get the estimated effect, which is an estimation of the true effect, which still remains largely unknown because of obviously you cannot be able to measure every single person in the population. Now, when we talk about grading, or when we talk about assessing the levels of evidence, so if it's very low, it means that the study appears to put out an estimated effect which is highly likely to be very different from the true effect. And as you go higher, uh, there's actually more approximation of the estimated effect on the true effect. And this usually reflects uh, good quality in the methodology and the good quality in ascertaining or measuring the outcomes. Okay. Okay, so we're now down to the last step in the whole SRMA process, and that is presenting or reporting the results of your SRMA. And we generally do this by means of a flow chart wherein we display how the studies that were retrieved using the literature search were selected. Okay, and we make use of our eligibility criteria for that. I'll show you an example of that, or a couple of examples of that in the next couple of slides. And we also report the results in terms of a table. So we actually must have a table that describes the characteristics or all the pertinent variables uh, from each included studies. Okay, again, I'll show you an example of that later on. We also we also report the results by showing the forest plot. So I already discussed that quite enough previously. And we also report or show the so-called funnel plot, which actually assesses the amount of publication bias there is among the studies that you have included in your SRMA. Now, if the results are dichotomous or if your outcome is dichotomous, then you also have to report the number needed to treat. Okay, so we already talked about, or rather, you already covered number needed to treat in a previous video, I believe. Right? Okay, so this is how a flow chart should look like. And notice that there are actually four parts to this. First, you have identification, then screening, then eligibility, then included. Right? So with identification, this basically involves getting the search results after you've typed in your search strategy on the search bar of the database that you're searching. So the database could be PubMed, could be Scopus, Web of Science, etc. Now, in meta-analyses, you have to search in more than one database. So you do not just limit yourselves to PubMed. Now, because you're searching in more than one database, you're more likely than not to get duplicate results. So part of identification is as you transition from identification to screening, you get rid of those duplicates, right? So you're now left with the number of studies or the number of records that you need to screen. Now, when we talk about screening, we're actually assessing the directness of the contents of these papers to your research question. Because sometimes with the even with well planned search strategy, you will still get search results that appear to have really no or really nothing to do with your research question. So you have to make those initial screenings, and if you see that a paper doesn't really have any relation with your research question, then you discard it. Okay. Then afterwards, you apply your inclusion exclusion criteria on the studies that are left, at least at this point. And you expect some studies to fail to satisfy your inclusion criteria and are actually satisfying certain exclusion criteria, so you exclude them afterwards. And you're now left with the final number of studies that you are to include in your SRMA, right? Okay, so here's another example. So it's showing you pretty much the same format or same pattern. Now, the point I want to drive here is you also have to include the number of studies at every single step. So notice in parentheses you have n equals and a number. So you have to indicate the number of studies that you were able to retrieve during the identification process, how many were left after screening, how many were left after applying eligibility criteria, and what would be the number of, or rather the final number of studies included in your SRMA, right? Okay, and here we have an example of the table of characteristics or the table of important variables that you need to describe in your SRMA. So in this table, you have to indicate or tabulate the pertinent patient or participant variables which you believe uh, may have a relationship with the outcome that you're interested in studying. Okay, so you have to detail them in this table, right? So it's a lot of work, but it's something that needs to be done. So you can pause this video and take note of the contents of each column. Usually the name of the study and the author would occupy the first column, and the second column would indicate the sample size of each study. Then the columns that follow would be the pertinent variables that you think may be related one way or another to the outcome that you are intending to study in your SRMA. Right? Now, if we have Consort as the tool or guide that you should follow when doing your RCTs, with systematic reviews and meta-analysis, there is actually a separate guide, and you call that guide PRISMA, or it's abbreviated as PRISMA. So it stands for Preferred Reporting Items for Systematic Reviews and Meta-Analyses, right? So this actually details the evidence-based minimum set of items for reporting in systematic reviews and meta-analysis. So here are the websites for that. So I highly recommend that you check these websites out, because it are in these websites you can be able to download the full and updated Prisma list or Prisma checklist that you have to satisfy, or to make that you have to go through to make sure that your meta-analysis or systematic review was done properly and of good quality. Okay. Okay, now we're down to the last stretch here. So I understand that you've already covered the possible sources of bias in SRMAs in a previous video. However, it is important to go through them again, because this is what you need to assess both with the use of the Cochrane collaboration and grade tools, right? Now, first, you have to be keen when reading the methodology and results and see whether the authors appear to be selective in terms of their reporting of the study results. Okay, so I have to assess for what's called reporting bias, okay, which is defined as a selective revealing or suppression of information, or underreporting for that matter. Okay. Another thing that you have to assess for is this so-called publication bias. So to define, this is the failure to include all relevant studies because they had not been published and were therefore not accessible. Now, this is a reality of research. There will be many journals, particularly journals that are of high impact, that favor manuscripts that report positive results. Now, it's always possible for a certain intervention to also have non-beneficial results besides beneficial results. However, this is not something that is attractive to journal editors. So a lot of times, negative results would be shelved or would remain unpublished, and that's a bit of a concern, because you would want to know both beneficial and non-beneficial effects of a particular intervention before we decide on whether to use it as standard of care for our patients, right? Now, to continue on with publication bias, so this also involves failure to include studies, or studies that failed to show a statistically significant difference between the treatment groups, right? Because it would less likely be submitted or even accepted for publication. So I think I stumbled a little bit with my grammar there, but it basically refers to the same thing that I explained just a while ago. Um, those that have non-significant results or negative results will most likely be left unpublished for the reasons that I discussed, right? Now, for that matter, journals would also prefer to accept manuscripts of studies that are of large samples, right? So if they are smaller samples, sometimes they get accepted, sometimes not. Again, it all depends on how well the methodology was, or how well the manuscript was written, and how well the authors were able to defend any challenges by the editors given to them. Right? And lastly, publication could have been influenced also by who funded the study or even the identity of the research group. Okay, you always have to, for that matter, you always have to look uh, into any conflicts of interest that were mentioned by the authors in the individual papers. So there's a particular section in each paper that talks about disclosures as well as conflicts of interest of the authors, right? So you have to look into that as well. Okay, so here's an example of a funnel plot. So Revman is able to generate funnel plots. This one I forgot to mention earlier on. Revman, however, is unable to perform meta-regression. So you will need the help of other software for that, as well as the help of a statistician in coming up with a meta-regression. Now, going back to this funnel plot, so first step in assessing a funnel plot is you look at the lower left corner of the funnel plot. Okay, so by the way, before I get to that, the funnel plot actually plots the effect size, which you see in the x-axis, against the sample size of each study. So you see that you see sample size on the y-axis, and each dot here in the funnel plot represents one study. Okay, now let's go back now to how you first begin assessing the funnel plot. It's recommended that you look at the left lower corner. It's actually the portion where there are negative studies or studies that report null values or negative results. Now, if that area is empty, then suspect some degree of publication bias going on, right? Now, you don't only look at the left lower corner of the funnel plot. You also have to assess for the symmetry of the points in the funnel plot. So again, just as a reminder, each point in the funnel plot represents one study, okay? Now, if there's symmetry in distribution of the dots along or around the midline, then the possibility of publication bias is low. But if you see points sort of clustering together, like what you see in panel B in this slide, then you suspect some degree of publication bias, and you have to report this in your results and discussion. Right? Now, additionally, you can also have language bias, right? So there's actually selective inclusion of studies published typically only in English, right? And oftentimes there's a tendency to exclude published material that were published in other languages. Now, you can actually be able to circumvent this problem by perhaps expanding your eligibility criteria to include even non-English publications, although this may entail some expense in terms of having a translator translate the publication or the article for you. Then lastly, you can have citation bias, which you also need to assess for and report if ever it's present. When we say citation bias, there's a tendency for those studies that are more frequently cited in the reference section to be identified and therefore included in the meta-analysis. This may have something to do with also with algorithms in the search engines that you will be using. Okay, so sometimes it's possible for some databases to make studies that are frequently cited be more visible or be more findable, for lack of a letter, for lack of a better made up word, in your search results. Okay. Now, before I end this video lecture, I should perhaps give you an overview of what the Cochrane collaboration is. So it's an international charitable organization based in England that was formed to organize medical research findings to facilitate evidence-based choices about health interventions faced by health professionals, patients, and policymakers. And they actually do a lot of, or they actually perform a lot of systematic reviews and meta-analyses for that matter. And these SRMAs involve healthcare interventions and diagnostic tests, and they publish them in the Cochrane Library that you can actually access online. Okay, now here's the logo of the Cochrane collaboration. So it's actually a forest plot right in the middle. So this forest plot within their logo illustrates an example of the potential for systematic reviews and meta-analyses to improve healthcare. Now, this is because there's some very important history behind this logo. I'll be talking about that in the next slide. Okay, now the forest plot that you find in the middle of the Cochrane logo was actually based on the results of a systematic review and meta-analysis on an inexpensive course of corticosteroids given to women about to give birth prematurely. Now, dexamethasone accelerates maturation of fetal lungs, decreases the number of neonates with respiratory distress syndrome, and improves overall survival in preterm delivered neonates. Okay, so the optimal gestational age when you give dexamethasone therapy, particularly for women undergoing preterm labor, is during 31 to 34 weeks of gestation. Now, the evidence on effectiveness of dexamethasone would have been revealed had the available RCTs been reviewed systematically around 1982. So it could have saved a lot of lives. And those at the Cochrane collaboration felt that this was actually a very important study to highlight. Thus, they included the forest plot for this study in their logo. Okay. And that ends this roughly 2-hour long video lecture. Now, as a parting note, systematic reviews and meta-analyses, while not involving actual human subjects that you have to personally derive data from, are still quite laborious to perform because you have to read and appraise the methodology and data of every single study you will include in your SRMA. And not only that, you also have to thoroughly assess for risk of bias and quality of evidence. Now, just as with other study designs, everything starts with a well-formulated research question and a well-designed protocol, even for SRMAs. And because of that, I strongly advise that you coordinate closely with your research preceptor if ever you decide on doing an SRMA sometime in the future. And with that, thank you very much for your kind attention and have a great day.